Once again, we will be looking at a power series. And the goal of this lesson is to replace our a sub n's of the power series with an equivalent expression, and that expression is going to be in terms of the derivative of this function. I know, that sounds very strange. So let's just start. Given this function, which comes from the power series, is differentiable and therefore continuous on our interval of convergence, then the following is true. So we are given this function, which is the same as above. If we take the first derivative, that's what that little 1 means. Let's see what happens. The derivative of a sub 0 is 0. The derivative of this is just going to be a sub 1, because that now becomes to the 0, and I just get that. Here the 2 comes down in front, and that becomes to the first power. Here the 3 comes down in front, and so forth. So that is my first derivative. Well, let's look at the second derivative. Again, that's 0. This would subtract 1 from that power, and so that would go away, so I just have 2 times a sub 2. And then here, this is where it starts getting interesting. If I multiply this down in front, I now have 3 times 2. Well, 3 times 2 is the same as 3 factorial, because that's 3 times 2 times 1. So that's where this 3 factorial comes from. And then, of course, times a sub 3 to the first power. I bring this 3 down in front. Now it's just 4 times 3. That is not 4 factorial. Let's look at the third derivative. Again, the derivative of that first term is a constant, so that's 0. The first term is a constant, so the derivative is 0. This is going to just leave us 3 factorial times the a sub 3. And here the 2, so 4 times 3 times 2 is 4 factorial, and so forth. So what's happening on the nth derivative, following this pattern, that's going to be n factorial, that's a sub n, and so forth. But let's look here. What if I let x equal to c? What's going to happen? Well, if x is equal to c, that's going to be c minus c, which is 0. So that would be 0, that would be 0, that would be 0. All the other terms, except for this very first term, is going to go away. So therefore, the first, or actually the original function, evaluated at c, all those terms go away, and you're just left with the first term. If you take the first derivative and evaluate it at c, all these go away, and you're left with just a sub 1. The second derivative, all those go away, and you're just left with that. And hopefully you can see the pattern. The third derivative, you're just left with that. And so the nth derivative, you would just be left with that term. Where are we headed with this? Hold on. So if we take this equation, if you will, and solve for a sub n, we get that. What does that tell you? So that tells you a sub 0 is the function evaluated at c over 0 factorial. A sub 1 is the first derivative over 1 factorial. A sub 2 is the second derivative over 2 factorial, and so forth. So what I told you we were going to do is, looking at here, we're going to replace all of those with things that look like that. And so that leads us to what's called the nth Taylor polynomial and the nth Maclaurin polynomial. The only difference is that Taylor talks about derivatives at c, and Maclaurin talks about when c is equal to 0. So we're rewriting our function in terms of our derivatives of those functions. So a sub 0 is now replaced with f of c, or f of 0 when c equals to 0. Then a sub 1 is replaced with f prime of c. A sub 2 is replaced with the second derivative divided by 2 factorial, and so forth, expanding on out to the nth term. So we're going to use these polynomials to rewrite these given functions in terms of a Taylor or a Maclaurin series. In previous videos, we've already taken functions and rewritten them as power series, but they had to fit the form of a over 1 minus r. E to the x, cosine and sine, they do not. We actually looked at the natural log of x. We're going to approach it a little bit differently in this video. So let's look at e to the x. I think I want to use the Maclaurin series and see if I can evaluate my function at c is equal to 0. But before I do that, it looks like I need to find some derivatives. So I'm going to let c equal to 0 and evaluate my function at c, which of course would be e to the 0, which is 1. But now I need to look and find some first derivatives, second derivatives, and third derivatives evaluated at c. So the first derivative is e to the x. The second derivative is e to the x. And yay, this is really easy because it's always e to the x. And when I evaluate those derivatives, they're always also going to be 1. Well, that's pretty easy. Okay, so looking here, I just need to rewrite my function. So e to the x equals my function evaluated at c, which is 1, plus my derivative, first derivative, which is 1 times x, plus my second derivative evaluated at 0, which is 1, but this time I need to divide by 2 factorial times x squared, and then keep going out forever. And that would express e to the x as a series. Let's see if we can rewrite that in function notation. So I'd have e to the x equals sigma, and I think I can just use that formula. That should work. If I put in 0, I get that. I get 1, 2, 3, and so forth. Remember, that's 0 factorial is equal to 1. So that's how we can write e to the x in terms of a Maclaurin series. But what about cosine and sine? I'm going to do one and you can do another. So again, I think I'm going to see if we can use Maclaurin and let c equal to 0. That always seems to be the easiest. So if f of x is cosine of x, evaluate that at 0 and you get 1. So the first derivative is negative sine of x, and my first derivative evaluated at 0 is 0. Okay, the derivative of sine is cosine, but I'd have to keep the negative, and so that would be negative 1. So here the derivative of cosine is negative sine with the negative, that would be positive. But I still get 0. Let's just do one more. So the derivative of sine is cosine, and that is 1. And so I've repeated the pattern, so it's just going to keep repeating. All right, so I could rewrite that the cosine of x is going to be, one more time, our function evaluated at c, which is 1, and that's really over 0 factorial, plus our first derivative. Well, that's going to be 0. And yes, that's going to be multiplied times x, but it's still 0. Then, plus our second derivative, well, that's going to be minus 1 over 2 factorial times x squared. And then we're going to have 0 x cubed over 3 factorial. And then we'll have plus 1 x to the 4th over 4 factorial, and we would keep going. I need to write that in sigma notation, so that pattern wasn't quite as clear. Let's see if we can figure it out. Well, if I look, all the odd ones are going to go to 0. So I'm just left with evens, right? And believe it or not, this is x to the 0, and this was 0 factorial. So let's see, I have x raised to an even number. So let's see, that might be to the 2n. And then I have even factorials, so that looks good. But the only thing I haven't compensated for is that this is positive, this is negative, this is positive, the next one's going to be negative. What's going to make it go negative, positive, negative, positive? You know, negative 1, but to the nth power, will that work? If I plug in 0, I will get positive 1, and I would get this first term. So that works. And so that's what the cosine of x equals to in terms of a series. My challenge is for you to go and now do the sine of x. You can repeat the process you just saw, or you could use the fact that the integral of the cosine of x is equal to the sine of x. So just like in the last video, you could actually take the integral of that series. Now, speaking of the last video, we did rewrite that in terms of a power series, as in we rewrote, I think we had the natural log of 1 minus x or x minus 1. So we could do it that way. But let's see if we could use the Maclaurin or Taylor series. So if I let c equal to 0, the natural log of 0, oops, that's undefined. So I can't use that. So I'm going to have to find another value of c. What if I let c equal to 1? Is that okay? So f of c, the natural log of 1 is equal to 0. So that's okay. So when I'm rewriting my series, I won't have x and x squared and x cubed. I'll have x minus c squared, x minus c cubed, and in this case, c will be 1. Okay, so let's continue our process. So my function is the natural log of x, my first derivative, my second derivative, what's that going to be? Negative 1 over x squared. The third is going to be 2 over x cubed. The fourth is going to be negative 6 over x to the 4th. Don't see a really good pattern here. All right, but let's forge ahead. F of c, and remember c is 1, that's going to be 0. The first derivative at 1, evaluated at 1, which is my c. The second derivative evaluated at 1. Third. Fourth. Don't see too much of a pattern there either. That's all right. So the natural log of x is our function evaluated at c, which is 0, plus our derivative over 1 factorial times x minus c to the first power, plus our second derivative, so that's minus 1 over 2 factorial x minus c squared, plus our third derivative over 3 factorial, then our fourth derivative over 4 factorial, oops, that's still a 1, keep going. How can I write that in terms of a series? Well, let's see if I can do some simplification. So I have the natural log of x is, I have just x minus 1 minus 1/2 times x minus 1 squared. But let's see, what is this? Could I reduce that? That's 2 over 6, right? 3 factorial, 3 times 2 times 1. So that's 1/3. So I can replace this with 1/3. So that's going to be plus 1/3 times x minus 1 cubed. What about this? That's going to be 6 over 4 times 3 times 2 times 1. Well, I know that's 6, so that just leaves me 1/4. And that was a minus. Now I see a pattern. Look at there. This is to the first power. That's to the second. That's to the third. That's to the fourth. It's alternating signs. I think I'm good to go. So the natural log of x is going to be the summation from 0 to infinity. Okay, so I know it alternates. I've got -1 to the nth power. Then I've got x minus 1 to the nth power. And you're going, ooh, no, it starts at 0. But yes, if n is 0, all of that's going to be 1 times 1. So that does not work. How could I make that work? Let's see. What if I could do a couple of things? What if I added 1 there? Okay, so if I stuck in 0, that's 1. If I stuck in 0 there, that's going to be -1. That still doesn't work because I keep not getting that term. I get a 1 or a -1. What if I start this just at 1? Would that help? Let's see. So that would be to the first power. That would be +1, and that would get me there. When n is 2, I'd get a 2. 2 plus 1 is 3, so that would be a negative. So now I just have to take care of that denominator. Thank goodness. I was getting worried. So what do I need to divide by? So this was 1 factorial. No, that's not 1 factorial. That's just 1, 2, 3, 4. So it's just n. And when n starts with 1, I think we're good to go. So that is the series for the natural log of x.